Hello students, we are here on the third day of our 45-day crash course that we are doing for chemistry JEE. So we have started our chapter which is atomic structure in the previous class. So in that class we have studied the Bohr's atomic model and about how it was good for explaining most of the things. Then later we say that saw that it has some limitations because it considered both that of position and the position and the momentum to be calculated at the same time, but it was the opposite of this Heisenberg uncertainty principle, for which we will have the discussion today. So our first topic is here, which is the Heisenberg uncertainty principle. So this principle, when came into existence, it completely erased, means it's completely competent with the Bohr atomic theory that we were having earlier. So what does this theory says? So it was given by Heisenberg, and it says that it was impossible to calculate both the position and momentum of a particle simultaneously. So if you are given a time t, suppose we are given a time t second, and we are told that if you have to calculate the position and the momentum both at the same time simultaneously for a microscopic particle, then it is not possible to do so. Okay, so the more precisely one of the properties known, the second one will be measured less precisely. So I will discuss how this will happen. So it means that if we have uh, calculated one of the thing, that is either position or momentum precisely, then the other thing will have more less accuracy. Sorry, it will have less accuracy. The more precise we have the other one. So this is the formula here for the Heisenberg uncertainty principle. It says that the certainty in principle, the certainty in position multiplied by certainty in momentum is always greater than or equals to h by 4 pi. So this delta x represent the uncertainty in position, and the delta p represent the uncertainty in momentum, and this h here is the Planck's constant. Now suppose that this delta p is increased, that is the uncertainty in principle is increased, then this delta x will decrease, so that this value is close to this one. So this formula is not applicable to the microscopic and both macroscopic both. So let me explain you here with an example. So suppose we have two particles, or you can say anything that is matter. Suppose we have one electron here. So for the case of electron, this electron is very small. You can say if you consider electron as compared to an atom, then it is a pea kept in a football ground. So that much is the means complexity of its structure, and you cannot see atom at the first place with your naked eyes. Then imagine what must be the size of electron. So that much microscopic particle is electron. Now let us compare it with a table. That would be um, not good to compare it with, but I am taking an example so that I can explain that how uncertainty principle is applicable to both of this. But since this variation of size, we cannot see that uncertainty in case of larger objects. So suppose I am taking a car whose mass is something like 150 kg, and we know that the mass of an electron is 9.1 into 10 to the power minus 31 kg. So this is the mass of both of them. So if you consider here the formula of uncertainty principle, it is delta x into delta p greater than or equals to h by 4 pi. Sometimes, let me mention it here, that sometimes h cut is replaced, and the formula is changed to this. So h cut is equals to h by 2 pi. So if you write it further, it can be written as delta x delta p is h cut by 2. So it's the same formula, just we are using a different notation. So this h cut is a different thing. You will come to know the significance in the higher education, but now just take it that it is another constant which is h cut, and it is equals to h by 2 pi. So if you replace, you will get this formula. Now what is the formula for momentum? So momentum is equals to mass into velocity. So now we are replacing it with this delta m into v by h cut by 2. Now out of these two quantities, mass and velocity, Mass is fixed. You know that we can calculate the actual mass. There is no uncertainty in the mass. So this mass will be outside this uncertainty. So we will have m as constant. We can say here at constant. We can bring it here. So delta x into delta v is greater than equal to h cut by 2m. So you can see here that as we are increasing this mass is, as this mass is increasing, this whole quantity will decrease. So if we are increasing the mass, so let me represent it with a different pen color. So suppose we are increasing the mass, then since this mass is in the denominator, so this whole quantity will decrease. So h cut by 2m will decrease, means the product of both of this uncertainty will also decrease, as this is in inequality with this quantity. So if you compare the mass of an electron, which is in the order of 10 to the power minus 31, as to compare to the car, which is 151 kg, you can see that this uncertainty will become much less and lesser. It is absolutely 6 point. So if you know the value of h, so it is h is equals to this h is equals to 6.63 into 10 to the power minus 34 joules second. Now we are dividing it by a greater quantity, 2 into 150. For I am considering it for a car, so this is for car. Now if we consider it for electron, so it is of electron. I'm writing it here electron. So this is for electron. Sorry, car. This is for car, and this one is for electron. So now we are calculating it. So this must be in the order of somewhat 10 to the power minus 30. So this is a very small uncertainty. But if you compare it with the electron, so it will be 6.63 into 10 to the power minus 34 by 2 into 9.1 into 10 to the power minus 31. So this minus 3 cancel, and this uncertainty is very large as compared to the car. So for that reason, this uncertainty principle, Heisenberg uncertainty principle, becomes insignificant for this car and larger object like the same. But for the microscopic particle which have very small mass like the electron, or we consider the proton or neutron, this uncertainty principle still holds. So what is this reason? So why this uncertainty principle is there? So there must be some reason behind it. So let me illustrate it with an example. So what is the reason behind this uncertainty? So suppose we have a small electron here. So if you want to see this electron, then light must fall on it, means or the photon must fall on it, and it should then reflect back, and we will see the electron. So first of all, light will fall on it and transition will take place, and it will again emit light, and we can see that yes, the electron is there. Now since the mass of this electron is very small, so if we apply light on it, then its energy will change. So you know that energy is nothing but kinetic energy plus potential energy. And what is the formula for kinetic energy? It's half mv square. Now since this mv square value will change, though mv will also change, and momentum will change. So if you apply this rays on it, yes, for first thing, that since this electron is very small, we have to apply any light that has a very less frequency, so that it can interact with an electron and see it. Sorry, high frequency, so that it can interact with electron and we can see it. So if we increase this frequency, then the energy of that incident ray, E is equals to h nu, we know the formula. So since this electron is small, we have to apply a very higher frequency to observe the electron. So we will provide with a higher energy incident ray, and this will change the momentum of this electron, as energy is nothing but kinetic energy plus potential energy, and kinetic energy is half mv square, where mv can be considered as momentum. So due to this reason, we cannot determine the position and momentum simultaneously, because if we apply incident right, then it will change its momentum. And if the opposite case is taken, suppose we are taking a light that is having a less frequency, then we can just get the momentum. But the problem then came here with that, since that frequency is very low, it will not interact properly with the electron, and we cannot determine the position. So in this way, you can think about the uncertainty principle. Now let us move to its implications. So what is an implication? So first of all, I have just proved it that it is applicable only for microscopic particle. Means significant for microscopic particle. It is applied to larger object also, but it is not significant there. Now, yes, it fundamentally limits the precision. So we cannot get the precise value of momentum and position both simultaneously at a time. Now, what does this result in? So how does this dissatisfy with the Bohr's theory? So Bohr's theory first postulate was that electron revolve around the nucleus with a fixed energy and a fixed stationary state. Means that he was saying that we can simultaneously determine both the energy and the both the energy and the position position of the particle. It was the first postulate of Bohr's atomic theory, and this became the main drawback of it, because Heisenberg uncertainty principle was just opposite of it, because energy refers to momentum only. Energy is nothing but, in terms of momentum we can find the energy. So if we are getting the energy precisely and getting the position precisely, this means that we can get the momentum and position precisely. And this was the wrong concept about the Bohr atomic theory. Due to this, the Bohr atomic theory was failed. So this was the most major drawback. Other drawback were like the splitting of spectral lines in case of hydrogen atom, and also the splitting of spectral lines in presence of electric and magnetic field. That is, electric field refers to the Stark effect and magnetic field refers to the Zeeman effect. So those were the further drawbacks of the Bohr atomic theory, but this was the major one. Now this is the thing here. So this makes the thing probabilistic. So how does it make it probabilistic? So suppose if you are going to tell the position of the particle, then you cannot say, okay, this particle will be here or the particle will be there in an atom. Means the electron probability is not fixed now. You can just predict the probability. Yes, it may be here, it may be that, it can be 90%, it can be 95%, but you cannot say with 100% probability. So 100% is not a probability, it is a deterministic thing. So you cannot say with 100% assurance, yes, that electron will be found here. Instead, uh, you can find the probability of that particle, that yeah, it may be existing there. So this was the Heisenberg uncertainty principle. So many questions are coming from this topic. So basically this formula here is the important one. So the formula, you must be given that the uncertainty in position is this, and the uncertainty in momentum is this, and now sorry, the uncertainty position in this. Now find the uncertainty in position momentum. So you will put this for values here and you will get your answer. Yes, this is the h. So do not get confused with that thing, that h by 4 pi can also be written as h cut by 2. I'm reminding it one more time because it is important. Sometimes people get confused with this. Now one more thing. So this is just for knowledge. So as we know that delta x and delta p do hold this thing, uncertainty principle, energy and time have the same relation. So they are also h cut by 2. So this is just for information. You do not need to remember it. I'm just saying it for the time being. Okay. Now let us move to our next topic. So with this introduction of the Heisenberg uncertainty principle and the thing which we considered in the first class of atomic structure, that was de Broglie hypothesis, which considered microscopic particle both as wave and particle. Microscopic means this electron and proton both as wave and particle. So these two things were the major drawback to the classical mechanics, which were used at that time for explaining most of these things. So with this thing, this quantum mechanics become popular at that time due to the immersion of this dual nature of the particle. So first time, the thing called wave equation was introduced by Schrodinger. So this man was the first one who started this quantum mechanic thing, means who started this not started this quantum mechanic thing, who put a great idea in quantum mechanics was Schrodinger. So he put the wave concept with it and defined that he can now quantize the energy level and that is the magnitude of energy, and consider electron as a wave. So due to this reason that he was considering the electron as a wave, now he has to mention some equation that would explain it. So his equation was this. So this is the famous Schrodinger equation. So it is written as H psi equals to E psi. So yes, you can get just a blink of it, starting of it, because it is not that important. So it outcomes are important in the JEE exams. So what does this equation says? So let me make it quicker so you can get the concepts more clear, because you cannot just learn these things by getting the answer, because people get confused as why this quantum numbers are here, this principal quantum number, why are they here, from where they came. So let me give you a brief overview. This psi here is the this psi represents the wave function. So this is the wave function, and this h here, you can consider h as something, it is like a tool which will operate on this wave function so that we can get our energy back. So here it is called as operator. So if you want to get a more clear idea, means a rough idea about it, so suppose that yes, that d by dx is also an operator. So what does it do? So suppose you are given a wave function like x square, it operates on this and give the value. So in the same way, this h, or this is called as Hamiltonian, this operates on this wave function and give us the energy and the wave function back. Okay, so do not get very deep into it. It is just for information. So it will be used to explain that why this quantum number exists. Now, since we are operating this Hamiltonian operator on this wave function, then we are getting the energy, and this energy was used to identify. Yes, this energy was used to identify. So the identify that where the electron will increase, means increase. What is the where is the probability will be more, and the quantum numbers which we have today, the principal quantum number or the azimuthal quantum number or the spin quantum number, came through this wave function. So same thing is written here. This yes, H is a mathematical operator called the Hamiltonian that operates to give the total energy, and I is the eigenvalue. So do not get into it. Just for information. So I is the eigenvalue. Now let us first discuss about this psi. So what is this psi and what is the psi square? So if you someone asks you that yes, explain what is psi, that what is significant physical significance, so it has no physical significance. It does not represent anything in the real life or in the electron. It does not say anything. Means it is not so useful. You can say that it has no physical significance. So psi has no physical significance. Physical significance. Whereas this psi square, this is important. So this tells about the probability of the thing, probability density. So this psi square has a physical significance. It tells that what is the probability of finding an electron in the given space or a given vector, you can say. So this has some physical, this has a use in the quantum mechanics, this psi square. So we will later on see that how this psi square is important using a graph. So it is written, the same thing written here, that psi has no physical significance, and it represents it does not represent anything, while psi square is known as the probability density. And what does this probability density mean? So it is the probability of finding an electron at a specific point in an atom. Yeah, one more thing here. So regarding the sign of psi square and psi, so we will use this concept in the later on classes. Then when we will plot graph of psi square versus the radius. So since this psi square is the square, so it will always be positive. So it is obvious. So suppose you are given a number like -5 or +5 or anything. So this must suppose is the psi. So if you take the square of that number, so it will always be a positive number, until and unless that psi consists of a complex number. So that is a very that critical thing. It is not important right now that whether it will contain a complex number or not, but yeah, it can be negative in case if it containing a complex number. But for now, take it as yes, that it is a not a complex number but a normal number. So if you do a square of it, you will always get a positive value out of it. So psi square will always be positive, whereas psi can be both negative or positive, or it can be zero also at some places. So it must be sounding abstract right now, but later on you will come to know that what these things are, why I am saying this, it is zero or positive or negative. Yeah, so here it is. So we do have this four things about the physical significance, that psi is not physically has no physical significance, while the psi square has the probability density, and it represents the probability of finding an electron in a given space or time. Now, yeah, the last point, that the psi square is always positive, while psi can be both negative or positive. Now, we can see we are going to see the graph of psi square with respect to the radius. Okay, so let me explain it here using a. So before we see these points, let us see what is this diagram, this plot represents. So these are the different plots we have here. So this is our first plot. So for 1s orbital, so I'll let me explain after we get the grasp of the quantum numbers, of the four quantum numbers, then we will get this thing. So what is this quantum number? So as we solve this equation, so whenever you solve the equation, you get a solution. Yeah, it is obvious. So if you are given equation, suppose x minus 5 is equals to 0, x minus 5 is equals to 0, then you get that x can be 5. It is always positive. Yeah, it's positive. X is plus 5. Now suppose they're given another equation, that is x minus 25 is equals to 0, then x is equals to root under 25, which gives the value as plus 5 or minus 5. So this both can be a value of x. So similarly, the Schrodinger equation, which is h psi is equals to e psi, have some solution. It has some solution. And this quantum numbers, principal quantum numbers, and the azimuthal quantum numbers, or the magnetic quantum numbers, or the spin quantum numbers, they are the solution of this so-called Schrodinger equation. So when you will solve this equation and get energy, then you will get this quantum numbers. So we will go through this four quantum numbers one by one. So this is the most important topic right now. So for this lecture, that the four quantum numbers, what are this? What do they represent? What is the physical significance of these four quantum numbers? So let me make it. Let me give a quick overview of this. Then we will go in details in the later slides. So what is this principal quantum number? So it gives about the tells about the energy level of the electron. Azimuthal quantum numbers, it describes the shape. Magnetic quantum numbers, it describes the orientation, or the the orientation, and the spin quantum numbers tells about the electron spin. So let us start by studying each of them individually. So first is the principal quantum number. So if you are given an atom here, suppose that an atom, the nucleus is here, and we have different shells. So this is shell 1, this is shell 2, and this is shell 3. So this shell has some values, so I'm representing it with 1, 2, and 3. Now, if we move from here to here, that yes, that n is equals to 1, n is equals to 2, then n is equals to 3, then we are increasing the energy. It is obvious. We have seen in the Bohr's atomic model that as we are moving, then we are increasing the energy as we are moving from the lower energy level to the higher energy level. Now n is this value. So this value of shell we have n is equals to 1, then n is equals to 3, 2, 3, and so on. This represents the principal Compton number. And since as we go from one energy level to the another stationary state, then the energy of the shell is increasing. Due to this reason, it is called as the principal Compton number, and it represents the and it signifies the energy of that shell. So it is written here, same thing is written here, that the principal Compton number determines the energy of the and size of the orbital. The size of the orbital is not that deterministic by principal Compton number. It will be explained more clearly by the azimuthal Compton number. It identifies the shell, yes, that whether it is the first shell or the second shell or the third shell. Then with the third point here, that it represents the orbital. So this orbital concept is new, so we will get it to in the next slide when we get the azimuthal Compton number. And yeah, this is the same thing as the shell, that is KLMN. So you must have studied this KLMN in the 9th and 10th class. So yeah, so they are represented later on by the principal Compton number as equals to 1, as equals to 2, and as equals to 3, and so on. Now here we are with the second Compton number, that is the azimuthal Compton number. So this is also a solution from the Schrodinger equation we have. So what does it do? So it is the main deciding factor of the shape of that orbital we have. So before moving, what is orbital orbit? So let me define it clearly. So I have said that yes, we have a nucleus, then we have a shell here. So this shell is also called as orbit. So you can call this orbit also. Yes, orbit. Now for each orbit or each shell, there is a number of orbitals that is present. So if you consider it for the first one, it is the n is equals to 1. Now we do have the energy level here. Now we have to decide that where this probability will be maximum and how it will vary through this space here. So for that reason we have this thing called orbital. So where this orbital will be drawn or where this shape will take, there the probability of finding the electron is maximum. So for n is equals to 1, we have only one shell that we have the s orbital. S orbital. So this s orbital is round in shape. So this is the first shell we have. So it is the shell that is present, only shell that is present in the 1. As we increase the value of n from 1 to 2 to 3, the number of orbital in that shell increases. Yeah, that is right. So here's the thing. So we have here that it determines the three-dimensional shape of the orbital. So if you are considering the 1s orbital, it will have a sphere. Then we have p orbital. So we will see how the shape varies. Now this is the main formula here. So what is the formula said? So for a given value of n and l, we can have n values of l that will range from 0 to n minus 1. So how is it so? So suppose we have a value that is n is equals to 1. Then n will be from 0 to n minus 1. So 0. So n minus 1 will be 0. So n is equals to 1 will have one orbital, that is s orbital, and its value is for which the value of l is 0. So do we have the s orbital. Now suppose we move it from n is equals to 1 to n is equals to 2. Then what is the number of what is the value of L, possible value of L we can have? It can be 0, then 2 minus 1, 1. So two orbitals will be present here. That will be S and P. So two orbits will be present here, S and P. Now for n is equals to 3, n is equals to 3, we have 0, 1, and so the formula we are using here, it is 0, 1, 2, 3 to n minus 1. So we have 0 here only. Then we have 0, 1, we have S and P. Then we have 0, 1, 2 means 0, then 1, then 3 minus 1, it is 2. So S, P and D. You can also say that, so these are the value of L. So L can be 0 or L can be 1. Two values are possible for L. Similarly, three values are possible for L. L is equals to 0, L is equals to 1, then L is equals to 2. You can also say that whatever is the value of n or the principal quantum number, that much number of orbitals will be orbits will be present here. So n is equals to 1 will have S, then n is equals to 2 will have 0, 1, and n is equals to 3 will have 0, 1, 2, that is 3 and 3. So it is 3. So you can also call it as subshell. The most means good word is subshell rather than orbital. Orbital is something that is more complicated, so it is subshell. So we'll come to know what is orbital in the magnetic quantum number as subshell. So yeah, it is written here subshells only. So it tells about the shape of the subshells that we are having. So for L is equals to 0, so here are the diagrams of each and every subshell that we have. So for L is equals to 0, so for L is equals to 0, we have the s orbital that is spherical in shape. Then for the p orbital, for the means L is equals to 1, you can say, we have the p subshell which has 3 orbitals, that is px, py, pz. So how does this 3 orbitals came, we will see it later. So we can call it a p subshell, has 3 orbitals, that is px, py and pz. Then we have the d subshell which has for 5, that is dx, dxy. Sorry, if you want to know the name, I am writing it here. It is dxy, dxz, dyz and dx square minus y square. 1, 2, 3, 4, 5 and dz square. So these are the 4. So you will get to know the names. So if I write the name here, so this one is a dz square. dz square. And this one is so this is dx square minus y square. Now it is in the xz plane, so it will be, sorry, it's in the xy plane, so it will be dxy. It in the xz plane, so it will be dxz. And this is dyz. So this is the fourth orbitals that we have in the d subshell. So we have seen two things here, for three things here basically, but the orbitals one will be cleared in the coming lectures, means the coming slides. The first is the shell. So for n is equals to 1, the value of the principal quantum number is 1, then we have the first shell. Then the value of 2, then we have the principal quantum number value of 2, that then we have the second shell. Then n is equals to 3, then the third shell, then the fourth shell. Now in each shell we have the subshells, that is S subshell, then the P subshells, then the D subshells. And in that subshells we have the orbitals, which has p orbital, px orbital, py orbital, pz orbital. Then d orbital has dx x square minus y orbital, dxy, dxz, dyz and dz square orbitals. So this is the thing here we have. Now to get how this px, y and pz and py and pz came, Let us move to the another quantum number, that is the magnetic orbital quantum number. So what does this represent? So suppose we have the value of L is equals to 0. So for L is equals to 0, we will have, so let me write it here. So we have L is equals to 0. So if you want to calculate the number of orbitals in it, then you will use this formula. So it will be, so it is the formula for number of orbitals. So it is for the number of orbitals. So for the number of subshell we have n, that is the value of n, that will be the number of subshell. But for the number of orbital, it will be 2l plus 1. So L is equals to 0, that is for s orbital. We have 2 into 0 plus 1, that is 1 orbital. So S will have no orientation. So what is this orientation? So let me make it clear here. So if you see this diagram of S, it is not oriented in any direction. So whether you keep this sphere, no matter what is the way you keep this sphere, it will have the same shape. It does not depend upon the direction. Whereas this p orbital and d orbital are directional in nature. So it is lying upon the x-axis, it is lying upon the y-axis, and this one is lying upon the z-axis. So this is the difference here. Now, then we were on the how to define this azimuthal Compton number. Yeah. So here was the thing that we have 2l plus 1 value for a given value of L. So if you are given a 0, then we have the, then we are calculating the number of orbitals. So it is 2l plus 1, that is 2 into 0 plus 1. Sorry. Yeah. So the number of orbitals we have, it is 2l plus 1, for L is equals to 0. So if you calculate here, we put the values here. For L is equals to 0, that is for S subshell. Then we get it as 0, 1. Yeah. So if you take it for another thing, so S orbital, yes, then 2 into 0 plus 1, it will be 1. So if you take the another L is equals to 1, sorry, L is equals to 1, then what is L is equals to 1 represent? It represent S P subshell. P subshell. So if you put the value of L here, then it will be 2 into 1 plus 1, that is 3. So we will have 3 subshells. So which are Px, 3 orbitals, which are Px, Py and Pz. So number of orbitals. Now if you want to know what is the value of this all 3, then we have the formula, which is minus L to plus L. So for 0 there is no minus, no plus, so it will have a value of 0. Then we have this thing Px, Py, Pz, so it will have minus 1, 0, then plus 1. No, in the books it is written opposite way, so it is this thing. Yeah. So it depends upon the orientation for which we are taking. It is not a absolute thing. It will be mentioned in the question, but for the book thing, I am taking this as the value. Similarly, if we consider it for the d orbital, for the d orbital, the d subshell, that is L is equals to 2. So d subshell, we have 2l plus 1, that is 2 into 2 plus 1, that will be 5 d orbitals. So before moving to the last quantum number, that is the spin quantum number, let me again revise those things which we have studied for the quantum numbers. So first we have the principal compound number, that is n. So it defines that which shell we are working with, whether it is S, that is K, L, M, N, or N. So K, L, M, N, which subshell you are working. So it varies from 1 to 2 to 3 and so on. Then we have the azimuthal compound number, that is L. So the value of the n is the number of subshell we will have here. So for n is equals to 1, we will have one subshell, that is S subshell. L is equals to 1, we have S subshell only. For L is equals to 2, we have two subshells, that are S and P. And how does this varies from? It varies from 0 to n minus 1. So 0, it is 0, so it is 0, n minus 1, that is 2 minus 1, 1. For 3, we have 3. So sorry, here, this is wrong. Yeah, this is 1, this is 2. Okay, so S, P, and D subshell, that is 0, 1, 2. It is only 0. Then we have seen the ML, that is magnetic orbital quantum number. So what is this ML? So it represents the orientation. So it basically tells about the number of orbitals we are having in a subshell. So for L is equals to 0, we will have 2L plus 1 number of subshell, that is 0, that is 1 subshell, and its value will be minus L to plus L. So for this it will be 0 only. So we have only one S, that is S subshell only. So it has no orientation, it is as it is spherical in shape. Then n equals to 2, we have 2 into 2 plus 1, that is 5. So before that is for d orbital. So we have 5 orbitals of d subshell: dxy, dyz, dxz, dz square, dx square minus y square. Then we have L is equals to 1. So we have 2 into 1 plus 1, that is 3, which are 3 p orbitals, px, py, pz. So these were the three quantum numbers that we have studied till now. Now this four quantum number is about the electron. So means electron spin. So do not get confused that the electron is revolving. So children often get confused that if it is talking about the electron spin, then electron must be revolving. It is something not related to that, but it is a different concept. So I will not discuss it here. But do not get the wrong. So you do not get the wrong idea from this basic thing. That's why I have said that thing, that do not imagine that electron is revolving on its own axis or something like that. So it has this minus half or plus half value. It's a different thing. So for a given electron, it can have two types of spin, that is minus half and plus half. So the spin may be anti-clockwise or clockwise. You can say in that way also. So this is anti-clockwise, this is clockwise. So the value of the spin quantum number determines whether the atom can produce a magnetic field or not. So it is a this is for the higher education, so you do not get confused with it. So this is the thing here. So when a atom is placed in a magnetic field, so it depends upon that whether it is having a plus or minus half. The electron will react in that way. Now, before moving to this question, let me make some things clear. So I am giving you a formula chart here, easier formula chart to remember things. This is the L, this is the N, this is the ML, and this is the MS. So this is the spin quantum number. So if you want to know, then it values vary from 1, 2, 3, and so on. Then if you want to know what L, then its value vary from 0 to n minus 1. If you want to know what ml, then its value varies from minus L to plus L. And it has two values only, that is minus half or plus half. So this spin is an intrinsic property, so it depends upon the electron only. It does not depend upon the environment. So it is just that the spin, it is not a absolute property but a relative property, and it does not represent about the spin of the electron. It is not that the electron is revolving around its own axis on a given axis. It is not so. Yeah, we do have a question here. So it says that the maximum number of electrons that can have a principal quantum number of n is equals to 3 and spin quantum number ms. So we are given here that we do have a value of n is equals to 3. So for n is equals to 3, how many values of L are possible? So you know the formula. So it is simple. It is, so n is equals to 3 will have 3 orbitals, 3 subshells. That is 0, 1, and 2. So for the first subshell, the value is for value of number of orbitals is 2 into L plus 1, which is 1 orbital here. Then 2 into L plus 1, it will give 3 orbitals here. Then it will have 5 orbitals here. Now one more thing I have left, that this one orbital, that px or py or pz, this one orbital can have only with only two electrons, and this both electron in one orbital will have different spin. So this is the thing here. So you will get a more complex idea about it when you will move to the filling of electron. But for now, to get idea of this quantum number more clearly, I am giving this example. So take it for now that we have a given orbital. So for a given orbital, it can maximum number of two electrons are possible, and both of the electron must have opposite spin. So there are total number of how many orbitals? 5 plus 3 plus 1. So it will be 9 orbitals. 9 orbitals. And each of those orbital will contain 2 electrons. So 9 into 2, 18. 18 electrons are total possible. But the question says that it must have ms equal to 1 minus 1 by 2. Now since it is 18, so this will be, so if you know, this is half of this electron will have plus half and half of this have minus half. So 9 will be the answer. Now we will move to the next slide. So there is again a question here. So you should try it your by self. So it is the same question, but one more specification is given here, that it will have an ml value of 1. So you can solve this question by yourself. Now let us move to this thing that is called nodes. So if you see the diagram here, so this is the diagram here of psi square versus psi. Yeah, here. So you can see that two diagrams are possible here. So this is the first diagram for 1s orbital, and this is the second diagram for 2s orbital. So if you see the diagram here, so suppose it's the nucleus, it is 0, and we are moving away from the nucleus. So this psi does not have any physical significance. You can see clearly from this thing also. Because if you see the diagram here, it shows that the probability of finding the electron, so if you consider psi as something physically significant, then it shows that the electron is most of the electron is present in the nucleus, which is not possible at all because nucleus contain only protons. But according to this diagram, the nucleus is containing the maximum number of electron. Similarly, if you see the diagram here, it has the same difficulty that we have with the 1s. It has the maximum number of electron near the nucleus, which is physically insignificant. But if you see the diagram here, that is psi square, it has also the same difficulty. Yeah, here. But it has one thing that is good. So if you see here, so if you consider diagram of p orbital, sorry, yeah. So if you draw the diagram of p orbital, then you will see, so this is for the p orbital I am drawing. This is 2p orbital, psi versus r for 2p orbital. So I am making things clear that why this psi square is more significant as compared to this psi. And if you draw the psi, then it will be like this. So why is it so? Because I have told you earlier that psi square is always positive because that is the square of the number. Due to this reason, it never goes down this negative value. Means it does not go down this zero. But in the case of this psi, it gets a negative value. But physically, it is not possible because all of you know that probability can never be negative. So in this way, this psi value means this psi becomes physically insignificant as compared to this psi square. So we have the physical significance of psi square rather than this psi. Now we were discussing what are nodes. So if you see this point here, this graph is going to a minima. It is having a minima, that means the probability of finding the electron is minimum here. So this thing is called as node. Again we have here this thing, so it is not significant. So we will consider only those nodes which are below the before the maxima. So after maxima there is no significance for this node. Now this is the thing here. So it has one node. Now if we go back to our node slide, then there are some formulas for describing the total number of nodes, then the number of radial nodes, then the number of angular nodes. So I will make it clear one by one what is radial node, what is angular node, and what is radial node. So if you take 1s orbital, so what is the formula that is given to calculate the number of nodes? So it is n minus 1. So the value of n is 1. So it will be 1 minus 1. So for n is equals to 1, we have a 0 number of nodes. And in n is equals to 1, there is one subshell only, that is S subshell, and it has no nodes. And you can see from the diagram also. So if I draw the diagram here, so it is something like this. This is a 0, this is psi square, this is r. So it has no nodes. So after the maxima, there is no significance of this minima. I have told it earlier also. But if you go to n is equals to 2, then the number of nodes will be 2 minus 1, 1. That will be 1. So it will have one node. And where is that node? So if you see that there are two orbitals, 2s and 2p. So we have two type of nodes here. So before moving to what is the total number of nodes, so let me calculate it. So it will be 1 for, so if you get what is radial node and what is angular node, then you will get a better idea. So the radial node is n minus l minus 1 and the angular node is l. So what is this radial node and angular node? Let me move to a different slide for that. So for that thing, you have to get an idea of what is boundary surface diagram. So if you see a s orbital, suppose it's the s orbital, one s orbital, and if you compare it with a 2s orbital, so this is the 2s orbital we have. So I'm drawing a boundary surface diagram. So it is nothing but a contour plot. So most of students must have not have heard this term contour plot. But just take it now that yes, that is a real thing we are having. It is just the shape of the shape of this orbital. It is spherical, and this dots, wherever the dots have the more, then we have the more probability. So if we draw this dot for the 1s orbital, so if you see this, so this is the boundary surface diagram I am drawing. Okay, so the dots are uniformly distributed all over this sphere. So what does this mean? This means that the probability of finding the electron on the 1s surface is, first of all, it is there is no node, so there will be all means all the electrons, means electron can be found all over this place here, means all over the surface of 1s case. But for the case of 2s orbital, so if you calculate the number of angular nodes, angular nodes. So its value is n minus l minus 1. So 2 is the value for n. What is l here? Radial node. It is, sorry, it is a radial node. Then 2 minus 1. So 1 we have for this number of radial nodes we have. And for angular nodes, we have this formula, which is n minus l minus 1. Sorry, L. So whatever be the value of L, that will be the number of angular nodes. So the value of L for s orbital is 0. So angular nodes is 0. So let me make it clear what is angular node and radial node. So if you see this diagram here, so I will draw again a probability distribution. So it is again a contour plot, and this is the nucleus here. Suppose is the nucleus for this case. For this case, so here the probability is maxima. So this thing here, okay. So if you see around this thing, let me draw with a different pencil to get more things clear. Okay. So this circle around this, here and here. Between these two regions, we have a vacant area. And this vacant area has no probability of finding the electron. It is not zero, but it is very less. And this place is called as the radial node. And for 2s orbital, it is one radial node. Okay. So here is the thing, that is the radial node. Now what is angular node? So in 1s, so number of angular node does not depend on this thing called principal quantum number. It depends upon the azimuthal quantum number. For any s orbital we are taking, whether it is 1s, 2s, or 3s, or any other s orbital, there is no angular node that is present on s orbital. Whereas if we consider for a different thing, that is, suppose we are taking a different example of p orbital. So this is the shape of p orbital. This is a p orbital we have. So what is the number of angular nodes? Angular nodes. Suppose this is 2p orbital. This is 2p. X. This is oriented around x direction. Yeah, this is y direction. This is z direction. If you consider number of angular nodes, then it will be equals to the is the azimuthal quantum number, that is 1. So if you see this thing here, if I draw a plane here, then you will see that on this surface it is called a nodal plane. Okay, so this word are critical, to do not get confused. I'm just to get a greater idea of this angular nodes, I am introducing this word. So if you see here that the shape of this orbital is fixed, so for each of this p orbital there will be one angular node which will be in the nucleus side. So if you draw, so this is a kind of plane we have, so it is also called nodal plane. So on this plane, the probability of finding electron is 0 for any p orbital. Now, if we calculate the number of radial nodes, so radial node do depend upon principal quantum number. It is n minus l minus 1, which is 2 minus 1 minus 1. That will be 0. So 0 radial nodes are present here. Similarly, if you draw another, so if you draw this again, if you draw this contour plot, so the dots will be uniformly distributed all over this diagram. Now if you move to the another one, that is 3px, so this 3px will be greater in size. So as we increase the number of means other or principal quantum number, the size of this orbital goes on increasing due to the increasing energy. So again this thing will be common for all p orbitals, so there again will be a nodal plane here. So suppose this is in px direction, so it will be pyz direction. So this plane will be on the yz direction. Now if we similarly if we draw the contour diagram for this 3p, so it will be kind of like this. So if you see it here, there is again a region inside it which has no probability that an electron will be found. Similarly, this phase will be same, means this lobe will have the same diagram similar to this. So this is the 3px. So this is the same orientation, that is x direction. And if you calculate the number of radial nodes, it will be 3 minus 1 minus 1, it will be 2, till number of the radial nodes. So this much was for today's class. So if we move to this last question, you can solve it by yourself. So this is asked that we are this thing I have taught you earlier. So it says that you have to see that which of this diagram of probability versus and this probability. So let me make one thing clear here. That is probability is equals to psi square into 4 pi r square dr. So this is a different kind of plot. So which of this diagram will represent accurately? So let me do it for you. It is a difficult one. So if you see it here, you can see that this psi square is multiplied by r square. So for what is the value of r? In the initial case, it is 0 here. So for this reason, so if you multiply it by 0, this whole thing will become 0. So out of this diagram, which to have the 0 value of probability near the 0 origin? So it is this one and this one. and these two options are excluded automatically. Why? Because we are multiplying it by r, and r is the radius, and it is 0 for the origin, and if you multiply it by 0, this whole value will be 0. So this is 0 and this is 0. Now these two are remaining here. But this diagram can never be possible, because you know that psi square is a kind of sinusoidal curve. Means not a sinusoidal, you can say. It is type of exponential curve, and not something which is touching this thing here. And if you multiply this equation by this constant, its shape will of course not change, but its size will change. So this thing is not possible, because if you see the diagram of psi square versus r, then it was something like this. So if you are multiplying it by r, then its shape will not change that much. So this is the thing here. So this is the answer we have. Okay, thank you. So in the next class we will see that how do we fill these electrons, in what order these electrons are filled in these orbitals. Okay, thank you.